Okay. Mana pergi pensel dia? Okay, now we done with our exponent. How about our fraction of Mantesia is only like 1,0,0,0,0,0, right? So we're going to paddle to what? To where? Going to paddle to the right. So we are putting 1,0,0,0,0,0 until 7. 1, 2, 3, 4, 5. That is our answer. Okay, so first of all, what you need to do when you are having the value, it doesn't matter, maybe it's decimal, maybe it's octal, maybe it's hexadecimal, you need to know how to convert to binary. When you convert to binary, of course, you're going to get 1010, whatever number is 10, but you need to start with 0.1. Okay, you move how many movement, I don't know, it's depend on your alhamdulillah, and the value depend on the value, but please make sure you know if it is move to the left, you're going to add, if move to the right, it's going to minus, and then you're going to have the value to the power of something plus or minus. From here, you put the sign to this part, exponent to here, the value here. So these two things, there is a rule. First, you need to padding to the left. This one to padding to the right. Okay. Any question?
Yes, doctor.
Okay. What is this?
I mean, I think I get this, but do we move the radix point until we meet the first number? Is that correct?
You need to remember back our normalization process, which is there is several rules, which is after radic point is non-zero and before the radic point is 0. Like this. Before it is 0, after that is non-zero.
Okay.
Other question? Okay, if there is no question, we can move. I think it is quite easy. Only that later on when you play and learn on IEEE, sometimes you're going to be confused because there are a lot of format, and the normalizations for IEEE also slightly different. Okay. In this next subtopic about biasing exponent, why we need biasing exponent? Because just now we already have our format. We have exponent. Why we want it to be biased exponent? So here, this is used unless your IEEE standard is mentioned. Okay, please make sure you remember, if the question mentioned IEEE standard, you cannot use this. Unless it doesn't mentions, then you use this bias exponent. Okay, over here you can see one obvious problem with this model is negative exponent cannot be represented in your previous solution. If it is a bias exponent, then you cannot represent it. That's why we come with the solution of bias exponent. Okay, again, you already done this. Okay, you say, okay, it's quite easy for you to know step by step. But we are moving to the left. So it plus positive exponent. When we are dealing with negative exponent, there will be a problem. Maybe you can try it. The problem can be solved by using a bias exponent. So there is a few equation that you need to memorize, okay? Because this equation will not given in your test, in your final exam. The formats of this when you are applying bias solutions is similar for the sign, 1 bit. And then how many bits for the n bits later on you will be given, and also the significant and pantesa. The format is slightly different with the previous one. Only when you want to apply this bias exponent, you need to apply in the equation, following equation below. First of all, you need to know the symbol. The symbol for E, capital E, B is a bias exponent. How about N? N here is the bit of exponent format. And then we have bias value. Okay, bias value is also needed. We call as B to the power of n minus 1. That's why you need to know the n bit first before we can get the bias value. And then we can have the normalized exponent. Normally in equation, they will give you the value of n and also e prime here. Then you need to find EB. This value will be given and you will be given. You can find the B here and the value you just fill in. Then you get the EB. From EB, you fill in inside. So it's slightly, there are several steps. And it's depend on the question also. Sometimes it's give directly the B. Sometimes it's give a N. E prime normally is going to give. So you need to find the value of EP. Okay, that's why at the beginning of stage, when you are moving forward, you need to know and remember the equation. Okay, let's take a look what we have next. Okay, what is the purpose of bias exponent and what is basically bias exponent? Bias value. Bias value is a number near the middle of range of possible value that we select to represent 0. Normally for bias value, it is equal to, this is equation just now you already look into, whereby n is the number of bit for the binary exponent. Sometimes in the sentences hard for you to understand, right? After this, we look into the example. But before that, you can see here, positive value. Any number larger than 2 the power of n minus 1 in the exponent field, bias value plus exponent. If you have the negative value, any number less than 2 the power n minus 1 in the exponent field, bias value will be minus exponent. But it's okay. We look into the example. Just now you have how many steps only? First, you just do the normalization, you convert, and then you do the normalization, and you putting into the format direct. But now you have 4 steps. First step, of course, you need to change to the binary if the number is decimal. Similar also with the previous step, isn't it? Second, we need to normalize the number. Third, we change the number to bias exponent. And lastly, we can form it into the format for three-field sign, and then exponent, bias exponent, and another one is significant or fraction or mantissa. Okay, example, similar example. Just now you are looking into the example number 17. This is the answer just now we already come up with. But how when we are applying our bias exponent? First of all, over here, we can see that we are having our n value is 5 bits, n value for our exponent is 5. So we have 5 here. Remember back the equation for b equal to the power of n minus 1. And I already mentioned that n normally will be given, and it is the n value. It is not this value, okay? This is the n value. Just now you having 14 bits. This one is 5. This is 8, isn't it? So this is the n value here. When we play around the 14 bits, we put here is 5. Okay? That's why we get the b equal to 16. After that, I already mentioned to you that we have another equation for our bias exponent, which is EB equal to E prime plus with our B. E prime will always be given in your equation. Where is it? It is here. This is not N. Just now I mentioned, right? This is E prime. Okay? This is E prime again, and the N value is this. How many bits that you have? You have 5 bits for the exponent. This is the N. This is the N. Here again, repeat, this is the N bit value. And you have the first equation, b equal to the power of n minus 1, where we get the value of n, the totals of bit for our exponent. Second, after we have this value, we're going to have the value over here. And we have another equation. EB equal to E prime plus B. Where we get the E prime? This is the E prime. You need to normalize first, okay? Let's say the example, you were given direct value. You're not given with the decimal. Maybe you were given with like 1.10. Okay, like this, times to the power of 1. This is not E prime. Why? Answer me why this is not E prime. Just now I mentioned this is E prime, isn't it? This is E prime, yes. But this is not E prime. Why? Someone?
Is it because we haven't normalized the fraction yet? It's not
Yes.
normalized, so it's not E prime.
This is not normalized yet. You need to normalize first. You move to the left here, let's say 0.11 times to the power 1 plus 1 because you move to the left. So the E prime will be 2. Then this is correct E prime. Okay? You know now, right? Where is your E prime? Where is your N value? And how you can get your EB, which is bias exponent. This is the equation that you need to memorize. Okay, back to the example here. After we get the value of EB, we get 21. We need to convert it to binary. So 21, we convert to binary. Just convert it and place it to the bias exponent just now. And this one is just copy paste because the only difference is our bias exponent. Why we need that? Because it's confused. Just now we learned in here just exponent. Why we need bias exponent? At the beginning we already learned that it's only for if there is a problem later on, the exponent is negative. Okay, but this one we just follow for example that given. That's why you cannot see. As long as you just know that the purpose of you to move to this bias exponent formats, that it is because if there is a negative exponent, it's going to be trouble later on. You cannot use this normal exponent format. You need to use the bias exponent to get it. Okay. There is another example here. Let's redo. Convert into binary using repeating multiplication. Okay, sorry, this one is solution. Store the decimal number 0.25. This one. How to convert? This is decimal 0.25. Remember back how to convert a floating point to decimal. I hope if you don't know yet, please refer back your digital logic subject, okay? This one we learn in chapter 2, numbering system. For decimal, you can directly convert. If it is floating for a number, what you need to do? You need to do multiplication repetition, okay? Here there is an example here. I don't want to explain further because you already learned last semester. But here after you get this question, you will get this value. Okay, this value in binary. Because what we want the binary one. 0.01 times 2 the power of 0. This is our number for 0.25. What we need to do? We need to do normalization because this is not normalized and this is not our E prime yet. So, we need to do the normalization. After we do the normalization, we need to move to where? We need to move to the right. When we move to the right, 0 minus 1, we get this answer. After we have this answer, we can see, okay, the sign is positive. We put here. We need to settle first. Okay, this we can directly put to these significant and fractions. And about this EB, this is our E prime minus 1. Okay, our N is what? 5. How are we going to solve? B equal to minus 2 the power of 5 minus 1. I already mentioned N equal to 5. And we get 16. After that, we have the equation for EB, which is B plus E prime. Our E prime is minus 1. 16 minus 1. So we get our EB is 15. This is decimal. You convert it into binary and place it here. Similar things. Then you will get the answer. Padding to the left because if you convert directly 15, you will get 1111. And you will need to padding and put 0 in front here. While for this one, similar also, just now we already looked, put it here and padding 0 to the right. Okay, any question? Please make sure you understand before you can move to next because after this, the normalization also already different. Okay, so after this also is going to be different. So please make sure you stick first in your mind. Okay, this is how, the step, and so on. Here there is an exercise. You can try to do it. There is a few exercise related to positive number, directly given with the binary, and then you can see the bias is already given directly. Bias value. And this one is negative number. Following the formats of Reddit 2. Okay, this one is similar. So you just do the conversions, follow step by step. First of all, you need to, this one, there is a few steps. because you need to convert 33 to binary first and then convert this to binary. You cannot convert directly because you need to know and remember fractions and integer side cannot directly convert. Okay. Here also similar. You have the number, negative number, floating point number. You just need to convert to binary and then follow exactly the rules, E prime, and then what else? B and 2 and minus 1 and EB equal to B plus E prime. Okay, so that is about the beginning side for your floating point. After this, you're going to look into floating point, but in terms of IEEE. Mana dia? Okay, now we move to IEEE. Last time, if you still remember, IEEE, I said you slightly we're going to be confused because there is also normalization under IEEE, and you will be having 32-bit and 64-bit. Just now it's just 14 bits. It's quite easier for you. But for 32 bits and 64 bits, it's quite longer. Just now I asked you about 16 number 00. Also, you already confused. How come you want to go for 64? Okay. But normally we don't call it 32 bit. We call it as single precision. Double precisions in your question. Task 1 or might be final exam, it called as a single precision, double precision. They didn't mention about 32 bits or 64-bit anymore, okay? Unless lah might be there is like a question they just want to play around with. Whether you know or not, double precision is 64, single precision is 32-bit. Okay? For floating point, that is here on the normalization. So, please don't confuse. Just now, it's not IEEE. Now, it's IEEE. The normalization is slightly different. You can read it. You can see now why the number is 1 in front. Just now, you learn normalization is starting from 0. And then, after the radix point, it is non-zero. But here you're going to see there is number before the radix point. Okay, this is the normal format for the representation. For the standard signification notification is slightly different. You have -1 S. What is S? S is your sign, whether it's positive or negative. E prime is normalization exponent. This now is E prime's E prime is similar last time. Normalized exponent. After you normalize, then you can get the value, isn't it? So let's see first on the single precision. Single precision is what? 32 bits. See how many bits that you have. Just now it's very small. That's why I said to you after each subtopic, please make sure you really carefully understand. Then you can move to the next. Okay, because it's slightly much more advanced compared to the previous one. Okay, 32-bit. The format you need to remember. Sign 1 bit, exponent add bit. Just now is 5-bit, right? So it's already 8-bit. And then from fraction, or mantessa, and significant is a 32-bit. Why I always repeat this? Because in equation sometimes it's not called as fractions. Sometimes it's just called significant. Sometimes it's called mantessa. So you need to know all the term. Okay. The size of exponent fractions give your MIPS computer arithmetic and extraordinary range because it is going to be huge in range. You have 32 bits. The smallest is 2.1 times 10 to the power of minus 3. This one is make you confused because you know already it's base 10. Largest number to the power of 0 times 10 to the power of 38. This is the largest. So this is the range. And we call it as single precision. One word. Now you find words. Last time you find bit. Bit. After this, next chapter, you're going to play around with byte. And you will find out also about words. Bit. Normally one bit, right? For byte, how many bits that you have? I also forgot already. I think, okay. One byte 8 bit, isn't it? Okay, 1 byte 8 bits. One word.
16, Doctor.
16 bit? 16 bit ah? Why is it? Currently
Wait,
we have 32.
let me make sure. Wait.
16 bit. I think 2 byte. 2 byte. Yeah, supposedly it's 2 byte. It's 16 bit. But it called here, it is one word, which is single precision, 32 bits. I will double check, but normally it's 16 bit. Why single precision is set as one word?
Supposedly, it's supposed to be 2 words, Doctor, not one.
Yes,
So,
right. It is 16 bits for one word is 16 bit.
maybe error in the slides or something.
Okay. So you need to know on the conversions. Words, how many bytes, how many bits, because this is important later on when you play around with a stack. Okay, later you will find the stack, and then in terms of your coding, you have the dot data, dot code. Here we will play around with byte words, and you need to store all the value in the stack. If you don't know how long is the byte, how long is the word, how long is double word, and you cannot correctly fill in into the stack. Okay, so just be aware about the terms. Okay, it is a single precision for 32 bits floating point number. Okay, unfortunately, single precision floating point cannot be still possible for number to be large. So it having a overflow and underflow. That's why you come in with the solution for double precision, which is 64 bits. Okay, this is just a story why and why. That's why you need to have the double precision. Here is the format for double precision. Just now for 32-bit, you have 1 bit for sign, 8 bit for your exponent, and 23 for your fraction augmentesa. Is it 32? Yeah, it's 23. Okay. So you have like this. But for 16.4, now you have 1 bit for sign, 11 bit for your exponent, and you need to have 52 for your fractions augmentesa. Okay? Because it's quite long there, that's why it's continuous. 52 bits. So this is the range for the smallest and largest number that you can support in your double precision format. Okay, now let's take a look into the standard representation. Just now you see the format first, just to see how a single precision and double precision in terms of the header size. Now we look into the representation. After that, normalization. Similar also what you have learned previously on your normal floating point. Okay, mana tadi? Okay, let's see on the representation. For the representation, you can read this. This one, IEEE leading, make the leading 1 bit for normalize. Okay. After this, you look into significant. 1 plus your fraction. What is the meaning by this? And your single precision value is 23 bits. And double precision is 53 bits. Just now you learn it 23 for fraction and 52 for double precision. But now you can see here it's mentioned your significant need to add with 1. Okay, your significant add to 1 plus your fraction. And 0 has no leading 1. It will give the reserve exponent value 0. Okay, you can try to understand the sentences. It's not better for us to look into the example later on. Okay, this is the format for the IEEE compared to just now our floating normal simple floating point. It is slightly different. We have a sign, and then we have a fraction and number plus with our 2, and then we have exponent. Just as simple as that. But now it's already quite complicated. Okay, let's take a look into normalization before we go to our example. If you look this number, just now without knowing IEEE format, you said is normalized, isn't it? But why it is unnormalized here for IEEE? If you look over here, this number, if you don't know about normalization for IEEE, going to say, hey, just now it mentions that we should have after radic is supposedly non-zero, but this is not normalized. But IEEE is set normalized. So how on IEEE normalization? Okay, for normalization for IEEE, if there is only single non-zero before radix point, okay, only single non-zero before radix point. It means that let's say you have 2, 1, 1, 1. You cannot, because you have 1, 2, 3 non-zero before radix point. So you need to move 1, 2, 1, 2 until only single non-zero. Satu je. Only one number non-zero before your radix point. Okay, that is IEEE normalization. Different with just now. For simple floating point standard normalization, you need to have after your radix point is non-zero. And before that is will be 0, isn't it? But now, before your radix point, you need to have only one single non-zero. This is normalized. You can see here, before that, it is 0. So, it is not normalized. Before that, it is 1, which is non-zero. And it's only 1, which is single non-zero. Then, it's normalized. It is 1 only, which is single. And it is not. It is normalized. Okay, let's take a look example here. Okay, let's say for this part, might be I can call someone who did not open your webcam. Oh, lepas tu tiba-tiba nanti ramai buka webcam. Just now I see the name of Imran. Imran, you just open your webcam, right?
Yes.
Okay, now help me to do the normalization for this IEEE. For this number 1, you given with the binary, no need for you to do the conversions anymore. This is the binary value. What is the normalize for this? What we need to do? Maybe? You always can have your module to check.
I was muted. Sorry.
Again?
Bring the radix point to the left
Okay.
by 4 places.
Okay, wait. One by one. 1, 2,
2,
3,
4.
4. Okay, after that?
It will be 0.11011101. The exponent two times the binary sign for 7 once again.
Exponent?
The exponent will be 0111.
0, 1, 1, 1. This one is 7.
Yes.
Why is 7? Where you get the value of 7?
Because there's 7 digits
7.
in the there's 7 digits in the normalized
Which one?
normalized number
From here until here?
after the radix point.
1, 2, 3, 4, 5, 6, 7. Oh, okay. Okay, thank you, Imran. I ask your friend. Jack, is it correct or not?
No.
Which one is incorrect?
I think the exponent need to put 8 bits and the exponent maybe is 3.
Exponent is 3.
8 bit.
And
Is 8 bit and 00040 and the exponent is 40 and 0011.
0. Why all of you like want to make it in binary? If you don't know in binary, you can just set in the
3.
decimal, right? Because you can have either one. Okay, exponent is what?
So 3.
3.
3.
Okay, normalize, this is correct or not?
I write 1.101101.
Okay, this is the correct one because this value is for the first simple floating format. But now we are moving for IEEE. I already mentioned that we are having different process to do the normalization. And Imran, please make sure exponent is not the total bit of the numbers of the radix point, but it is the value of here. If you are moving just now, for your knowledge, might be you are moving 4 times, you're going to do times 4. So this is the value of your exponent. Okay, your exponent can be decimal, it can be also binary. This one we already learned in our previous class also. Okay, if you want to convert, no need for you to head it. You just convert. If you have 3, you can just convert 1, 1. Then you can put whatever number in behind, might be if it is a 8 bit for single precision. You precision 8 bit, right? So you can just padding to the I think padding to the right, right? 10000. Padding to the right, right? Huh. Then for fraction, then you can padding to the tersilap. Padding to the left. Sorry. Correct. So you just fill in until at bit. Okay. So no need to head about the exponent, especially when you are having the value in the decimal. Okay, only for the normalization is need to be in the in term of binary. I guess if because you are given in the binary value now. Okay, next. Might be just another one example. Okay, Abdul Kadir, you want to answer?
Yeah, doctor.
Okay, which one?
Okay, so we move it to the right.
B,
One, two, what?
B.
B, yeah, B.
Okay. 1,
2 times, yeah, 1 and 2.
2 times.
No, 3.
3 times.
Yeah.
Okay, now?
So this will mean that 1.01,
Okay. Then?
and our exponent is -3.
-3. Okay, because we are moving to the right. So our exponent is -3. Okay?
Yes.
Later on, you need to know how to convert -3 to also your binary. Okay? I think we look into only 2 example. You can try to do it C and D. After that, thank you Abdul Kadir for sharing
Good.
us how to do the B. Okay? Now, similar also, just now for the simple one, we have bias exponent. Just now you learn IEEE Dr. said it's only exponent. But we also will have the mana? Okay, we will also have the bias notation or bias exponent there for replacing our exponent because similar also problem. You can see Abdul Kadir mentions that it is -3 for exponent. Where we want to convert it and we want to place it into our add bit here. You can see 1111111. It will be a problem if we are dealing with negative exponent. That's why we need to learn on place it using our bias exponent. Okay. However, using second complement, you can do negative exponent look a big number. So this is a problem for us. Okay. That's why, what else? Okay. That's why we need to apply similar equation, bias exponent. But you have -1 here. And for EB, we have the similar equation. Only for the bias exponent, you need to have another one, -1. Just now, for the simple floating point, we have b equal to 2 the power of n minus 1. And our b is small. Okay. Now we have in single precision, it is 1, 2, 7. And a double precision is 1, 0, 2, 3. It's always fixed. Why? Similar also just now, our n value is fixed. Isn't it? Just now for 14 bits, we have our n value is 5. Similar also for bias value here, and our n is fixed. For 32-bit or single precision, our n is what? 8. And then for our double precision, our n is 11. Isn't it? So, where is the value? Okay, I show you. This is our n. For double precision, this is our n for our single precision. That's why your bias always will be fixed. Similar also to the previous one. We have 14 bits. The value for n is always 5. Okay. You can remember the value. No need for you to apply and etc. Okay. Over here, when we have the value of bias B, which is this value, we can apply it directly after we have the E prime value. Okay. Normally, E prime value, our problem when we are dealing with negative number. That's why when we do the negative number exponent here, we always get positive. That's why our number will be not too big as mentions like this, our problem. Okay, you can read it. What is the problem? So we need to have a solution. That's why we need to use a bias exponent instead just normal exponent. Okay, let's take a look in the example. Okay, example here, you were given with the value 1.0 times to the power of -1. It directly shows that it is normalized for IEEE. You need to look into the question. If the question mentions about single precision, your value of B equal to 1 to 7. If the double precision is 1, 0, 2, 3. Okay, later on you can apply. First, we look into the single precision example. So what we need to do, first we have the sign. It is a positive number, so we put 0 here. After that, we have 8 bits for our bias exponent. This is the value for my fraction. I will put here. Here, and then padding to the right. Okay. Next, our exponent. Bias exponent E prime plus 1 to 7. Our E prime is this value. So we will get 1 to 6. We convert to binary. Alhamdulillah. We will get 11111110. Okay, this is the things that we will get. Kenapa macam terlebih ni? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 8? Can you double check? 1 to 6 is what? How many 1? Digit 1.
6, Doctor.
6, right? I think in the slide here, you can correct it because there is no 1 there here. Okay, so you will get 1111110 for 1 to 6 convert to binary. So you can see it is only 7 bit. You need to padding to the right of the 0. Okay, to the left, padding to 0. This is the value for your bias exponent. If it is 16 4 bits, if it is 16 4 bit, you're going to have 1 bit, 11 bits here. Here will be 52. Correct, right? 52. And our value of EB will be 1, 0, 2, 3. It will be 1, 0, 2, 2. You convert to binary, please. 1, 0, 2, 2.
Shall I say, Doctor?
Yeah.
It's 0, 0, and 1.
0, 0. No 0 in front. 1, 1.
Okay, 1, 1. Then 1, 2, 3, 4, 5, 6, 7 ones.
7, 1.
Yeah, 7 ones.
Sorry.
Another
7, 1. 1, 2, 3, 4, 5, 6, 7. Okay. Then
8, 9, because you deleted the first ones. Add 2 more. 1, 1. Yes. And then there's 0 in the end on the right.
Okay.
Yes.
I don't know whether it's correct or not. Please, the rest check also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 bits here. So you can, mana yang letak? I letak sini lah. Okay, for this one is a single precision. If it is a double precision, you will have 0 and then you will put 11 bits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it is not enough 11 bit, you need to padding to the right. Okay, this is your value. And alamak, dah delete. Okay, and then this one you put here 1 and padding 0, 0, 0, 0, 0 until 32 bits. That's for your double precision. Okay, any question? So that is the difference between single precision and double precision. Okay, you can try to do the exercise when you are dealing with bias exponent, and you need to find out the bias exponent value for single precision, double precision. You can see here, you can have the decimal, and then you need to convert to binary, decimal and binary. Please make sure, remember the B here is already similar, and only the value of E prime is given. So you can try to do the bias exponent. Okay, let's take a look into the example. So before we go to example, you need to do step by step how you can convert the decimal number to your binary floating point. Following the format lah. If that is a single precision, you need to follow the formats of single precision. If it's a double precision, you need to follow the double precision format. Okay. You need to do step 1, normalize first. You check first, is the decimal number already normalized or not? First, your decimal number you need to convert to binary. Is your binary already normalized or not? And then, you're going to determine the sign bit. After that, determine the bias exponent. And lastly, your fraction value you're going to put. Let's take a look on the example. Please help me in converting, okay? Because I don't have calculator and I'm too lazy to convert. First, you have this value. Please convert 10 to binary, 0.5 to binary. What you will get? I think this one, okay. It just asks you to normalize first. I think it's not going to, yeah, it's asks you to convert directly first. Okay, you need to convert 10 to binary. 0.4, what you need to do? You need to do the repetition multiplication. How many that you will get? 0.4 times 2, and then what you will get. You can try to do it, then that is your answer. Then you combine with this 0.0110. This is the value for this number. Please make sure you know how to do conversion. Okay, this one you already learned in the digital logic subject. If you still didn't remember how to do repetition, when you're going to stop, and etc. So please do back recap on your digital logic, because this one is important. Normally in question, it will come out whether it is a single or double precision, but we will always give you a floating point number because it's going to be slightly tricky. Rather than we just give you a digit number, isn't it? Okay. We have the value now. Alamak, direct lah. Okay. We go by one by one. 1010.0110. Okay, what we need to do? We need to do normalize the bits. Where should I go? Left or right?
You go left, doctor.
1, stop.
3.
2,
Yes,
3.
3.
Okay, I move 3 times to the left. 1.01001110. Okay, that is the value that I will get. 2, 0
Positive.
plus
Plus 3.
3. So we will get the answer like this. Okay, let's check your answer. Correct or not? Okay, this is only the first step. First step, you need to do normalization. After that, what you need to do? You already have the value of what? This is what?
E prime, doctor.
E prime. Yang lain mana suara ni? This is E prime. So we have a E prime. Wait, I want to... Okay, it's quite hot here. I think because it's already 3 p.m. Okay. Sorry, I cannot stop because this is not a theory things. It's not boring. This is, I think, more to mathematical. So let's do it together so we can just like continue, okay? Okay, this is our E prime. Next, what we need to do? Of course, we need to find the EB, of course, right? Exponent. That's why we need to know that here is how many bits? This is single precision.
32, doctor.
Yeah, it is 32 bits. Next, you need to determine the sign value, of course. Kat mana dia pergi? Okay, let's redo here. This one, 1 bit. Your bias exponent, how many bit? For single precision?
8.
Oh, 8 bits.
8 bits.
The rest will be
23.
23 bits. Yes. Okay. Here we already know our sign is positive. Positive will be 0. Then we want to know the EB. Here you can directly already fill in the value of your fractions. But your fraction will be slightly, you can see there are a lot of things. You can put it here and after that you can padding to your right. Later on we do it because that is the last step. Now we want to find the EB. Okay, EB equal to, sorry, this one is a capital letter, okay. EB equal to E prime plus B. Your E prime is 3 plus single precision. How many? 1?
127.
127. Your E prime will be
130.
130. Please convert 130 to binary.
It's 1.
Wait. Let me find someone. Daniel. Chat Daniel. What is 130 in binary? Chat Daniel. All of your friends are helping to do together. What is the value? Okay. Anna, what is the value? 130. Convert to binary. Anna, are you here? Okay, again, what is the value of 130? Someone help me? Abdul Kadir?
Yeah, doctor. So it is 1, 3 zeros, then 2 zeros, 1 0. Yes.
1, 2, 3, 4, 5, 6, 7, 8. Okay, it's already 8. So you just fill in later on to here, isn't it? Okay, next. We can see this is a correct answer. Okay, similar. Now you going to place this fraction for serabut. Okay. Now you need to determine your fraction. Okay, fraction. There is several things. You need to drop the leading 0 in the fraction. Okay, you need to drop the leading 0, leading 1 in the fraction here. You need to drop and you need to pick the rest and putting into your format. Okay, this one you need to padding to the right. Okay, that is the correct things to do for the IEEE single precision. If it is double precision, you're going to make it until 52 bits. Okay, that is the only difference between your simple floating point. Previously you learned in your class yesterday. Okay, any question? You have several exercise you can do it. Exercise 2.3, exercise 2.4. You play around with the positive and negative number also. Maybe you can try to do also similar if it is a single precision or double precision. It's both is similar, only in terms of the format. The only different, double will be 11 bits and here will be 32 bits, and the value of B also different. Okay, this one convert binary 14 point. Okay, after you already know how to convert your decimal number to binary, now when you were given your binary 14 point, your number just now like this, too many long number, you need to convert back to binary. Let's say for this one, just now we have example, right, like this. But this is from the value of decimal. You want to get this format. But by giving this format, you need to go back from step 4, step 3, 2, and 1 until you find out this. So that is the several step for you to reverse back your step just now.
Hi, Doctor.
Ya, I nak tengok kejap. Diorang kat lobby ke tak? Diorang masuk balik ke? Dah hilang. Ana. Okay, you can answer. Ask me question.
Why did we drop the leading one of the fraction?
That is for IEEE only. IEEE, that's why we start with the 1 there. Sekejap mana tadi? Kenapa tak gerak? Okay, that is the for you to find out the fraction for your IEEE format, single precision and double precision. That's why for IEEE we start with 1. For the simple, we start with 0. That's why we just pick here without we concern about the value in front because it is 0 already. But for the IEEE, in front of it is 1. So we need to put and ignore it. It's mentioned as a drop the leading 0. Okay, right? Right? Hello.
I think this is just the rule
Okay.
for the IEEE.
Yeah, that's just a rule because just now if we are simple versions, we didn't have this rule because starting we are at 0. Our number is starting at 0, isn't it? So that's why we ignore. Maybe we can also set it's not a drop. It can also ignore. It's just a rule. We just need a floating value number. Okay. Now we are moving to from binary floating point. We need to convert to decimal. Whether it is single or double precision, the step is similar. So let's take a look one by one. You can look into the step. First of all, when we are given with the value, what we need to do? We need to see the value of this first sign. So now it's 1. Our sign is 1 means that negative number, isn't it? So it is a negative number. Step number 2. We need to extract our value of our exponent, bias exponent. Please convert this to decimal. Anyone convert this to bias?
Okay, doctor, it's 129.
129. This one.
Yes.
Okay, this is in your binary. And if you still remember, EB equal to B plus E prime, isn't it? You don't know your E prime yet, but you know the value of B, you know the value of EB. What is our B for single precision?
127.
127 equal to 129 plus E prime. What is the value of your E prime?
We minus 127.
We will get 2. Correct?
Yes.
Okay, so we get our E prime as 2. So we know that it will be to the power of 2. We don't know what is the value in front. How to get the value in front is here. So let's take a look step by step. This is the things. Just now we already know this value. And then, oh, this one is already fraction. Okay, after that, from here, we can get the value of our exponent. It's not showing here E prime. It's not showing the E prime yet. Okay, from here, you were given the value of your fraction. From this part, it is the value of, supposedly you will get 0.01 times 2 the power of 2. But this value in binary, you need to convert this to decimal. Alright, right, 0.1. Okay. So you need to convert it into the decimal. So you will get, you convert it, this one is how to convert 1 times 2 the power of negative 2. You will get 0.25. Extract the value of fraction. But I already lost here. After we get the step number 2, we will need to know the value of our fraction. Okay, our fraction extraction. We need to extract the value of what we have, 0.01 times to the power of 2. So might be we can move this 1, 2. Why is negative 2? Is it negative 2 or 2 for the value? E prime equal to
It's positive, doctor. I don't know.
positive. Supposedly we will get 0.01 times to the power of 2. If we want to move here, and then we will get 0 to the right, negative, right? So
Yeah.
0. Why it is 1 times to the power of negative 2?
Isn't it 0.01 to the power of 0
0.01
times to the
Times
power
2
of
times
0?
to the power of 0. Yeah.
It should start with to the power of 0
Why?
and then
Because this one is we need to have the normalization, right?
we normalize it into 1.0 times to the power of negative 2.
Or before it's normalized, or
Yes, that
right?
is unnormalized.
Okay, now we have 1, 2 to the right. It will be negative 2 because we go to the right. That's why we have 1 times to the power of minus 2. Is it? Okay, thank you for correcting me. Now here we're going to get the value, and this value we convert it to the decimal. So we will get 0.25. This is the decimal value. But now we still not yet apply in our format, IEEE format. Basic equation for IEEE. So we have a prime, we have the sign here, and also the fraction. Now we have negative 1. Our sign is negative, right? 1.
Yeah, 1.
Okay. Times with 1 plus 0.25 times to the power of 2.
Minus.
2. And we have negative 1. Of course, is 1 plus times with 1.25 times to the power of 2. This one you can solve this. And you will get negative 1.25 times to power of 2. Let me see whether my answer is correct or not. Negative. Yes, it's correct until here. Then you can solve the solution. Mine is until here, right? Then you will get negative 1.25 times to the power of 2. To power of 2 is what? Is 4. 4 here times with negative 1.25. Then we can solve it. We will get negative 5 decimal. Okay? So you need to look step by step. Again, we go for this question. First is our sign. Step first is our sign here. Second step, we need to have the E prime value. After we get the value here, we convert to the decimal. And then this one we know is already fixed, and we're going to do E prime equal to EB minus B. Then we get 2. That's why later on we will apply. Step number 3. We pick this. It is still not normalized. We have 0.01 times to the power of 0. We can try to do it normalization, or maybe we can directly find the value. What is the value of to the power of 0? 0.01. You will get the negative 0.25 decimal. After that, step number 3, you apply the value into the equation. This equation is slightly different as I mentioned in the beginning. You already know the value of E prime. You already know the value of your fraction. You already know the value of S. So you just apply in -1. Here is 1 times with 1.25 times to the power of 2. So you solve this, you're going to get your answer -5 decimal. Okay, any question? Is there any example? This one is just exercise, not example. Maybe we can try to do it together. Before that, for this example, any question? Okay, if no question, maybe we can do together for this one. First step, what we need to do? First step, Nurdini, what we need to do?
Need to extract the value of sign.
Okay, thank you. The value of sign is 0. Isn't it? So for second, we have the value of our base exponent here. What is the value in decimal? Nur Suhaida, convert this to decimal.
Do it
Again?
-2.
Huh? EB, not E prime.
Huh?
EB. This one, you just convert this to decimal.
I convert in the calculator, I got -2.
Seriously, you get -2? Shi Junhui. Junhui, what is the value?
1022.
Is this big?
Uh,
Oh, this one is double precision. Okay. Understood. Okay. 1022. Correct? Correct or not? This value you convert to decimal. Betul ke tidak ni? Ya Allah.
Yes, Doktor.
Yes, Doctor.
Okay, correct. Okay. Now we need to have E prime. EB minus B. What is the value of B for double precision? Double precision?
1023.
1023. I tak nak check. Okay, 1023. So, you will get 1023 minus 1022 equal to -1. Okay, done this part. Number 3, what you need to do? Fraction. 0.01 01 times to the power of 0. 1 times to the power of -3. So you can solve it, get the decimal. What is the value? -3 to the power of -3.
0.125.
0.125. Okay. The rest, is it correct or not? You can check, okay, later on. After that, we have already get this. We going to apply it into the equation. -1, our sign is 0. Times with 1 plus 0.2125. Lagi apa? Times to the power of E prime, isn't it? E prime kita -1. Correct tak I punya format ni? Is it correct, my format?
Correct,
Yes, Doctor.
Okay, then you try to solve it. Okay, the most important is the step. If you know already the step, whether it is a single precision or double precision, you can answer it. Okay. Let me go a little bit je. Kita habiskan 2.5. Might be, I think it's not too long. We have plenty of time. Plotting point arithmetic. We look into additions and multiplication. Okay, this one you can try to look into, and there is another flowchart for you. But for me, you can try to look into the flowchart, but there is also a step by step that you can follow. Okay, you need to assume 4-digit decimal digit for fraction and 2 decimal digit for exponent. Okay, in the beginning, kenapa dia dapat macam tu? For addition and subtraction, just now you learn multiplication, subtraction, right? It is necessary to ensure that both operand are the same exponent value. Yang ini you already learn in your standard, I think, might be standard 6, darjah 6 pun dah belajar, I guess. For you, let's say you want to add two number, okay? You want to add two number. 1.2 times 10 to the power of 2, let's say. Plus 1.2 also, but you times with 10 to the power of 3. How are you going to do? You need to make sure the exponent is similar first, right? Then you can add the value, isn't it? So similar also in this COA subject, you need to make sure that the exponent value is similar first, then you can do the addition and subtraction. Okay? And it's going to make you do the shifting value. Because like this might be, you want to go and change this to 3. You can also change this to 2. It's depend on you. As long as later on after that, you can normalize it back. Let's say I add to it to be 3. I need to be at 1. Kalau tambah, it's going to go to the left, isn't it? So it will be 0.12 times 10 to the power of 3. Now I can add them together. Plus 1.2 10 to the power of 3. I will get 1.32 times 10 to the power of 3. Sorry. So this is how you can do. Might be you can also look into vice versa. Ada terdelete pula. How you going to shift your radic point. And then for multiplication and division is more like straightforward. So this is addition flow. For bias exponent range, for you single precision and double precision. Let's take a look into if you have the question for this example. Addition. This one macam dah balik sekolah menengah dah. We back to our secondary school. Adding two decimal floating point. Assume that we store only 4 decimal digit. It's already mentioned, okay? 4 decimal digit of the significance and 2 decimal digit for exponent. So 4 digit for decimal, significance and exponent, 2 decimal digit. Okay, let's check. Can we directly add this? Cannot. Why? Because the exponent is different. Seriously, this is a secondary school, I guess. How are you going to do? You're going to make this exponent similar. You can have a choice. Might be you can make it smaller and also bigger in your previous normal mathematical. But in the COA subject, it asks you to go for the smaller exponent. Okay, for this part, which one is smaller? This is the smaller, which is -1. That's why we need to change this to be smaller. Okay. Sorry. We want to align the decimal point number that has the smaller exponent. Betul lah. -1. This one is plus. Oh, we want to go for the biggest. Dia punya ayat pun buat orang confused. So for here, when we have the smallest need to change to be the biggest. Actually, it's either wise, because the most important later on you need to do normalize. Okay, you can have the smallest and biggest, normal mathematical. Okay, for this, you were given from smallest, you want to make sure it's similar to the biggest one. So you will move to positive. Positive move to left. How many? You need to get 1. 2 times. 1, 2. So you will put 0, 0 in front. Then you will get like this to get 10 to the power of 1. After you get similar exponent, then you can directly add. You can also do the reverse way, which is negative. You can change it to be -1. Okay, you can just add it and you will get 10 to the power -1. The answer here, later on, you can do the normalization. Similar, okay? For step 2, you already add. Step 3, you need to do normalize the summation. That's why you can do at the negative or you're going to go for the biggest or smallest also can, because later on you do normalization. This is normalized or not? Not right. So IEEE, where you going to do? You're going to go to the left here. Stop until here. We have 1 in front. Then we already have normalized. In the equation is mentioned for fraction value, it is only until 4 decimal digit. 1, 2, 3, 4. So until here only, then you just ignore this one. That's why you get this. You check again whether after you do the round fraction, is it normalized or not? If it is normalized, no need for you to normalize back. That is your final answer. I hope no one get wrong answer for addition and subtraction, because this one is normal mathematical, not touch the COA subject. Unless in terms of normalization is okay for you, but normalization is also not too hard. Addition is most important. If you wrong at this part, I don't know. Okay, next example. You were given with 2 binary floating point number, and it is slightly tricky. You can see 0.2. How you want to convert this to be like times 10 equal to 0. Okay. For this one, 0.5, you know it is a 10 to the power of 0, because it is decimal number. You need to convert this to binary. So to convert this to binary, you need to do a repetition multiplication. Then you will get your answer. What your answer will be? You will get this one. Okay, you try to do it, convert the decimal value to binary. Similar to this one, you're going to do repetition multiplication. Basically, it's similar. But here you're going to stop because of what? Check back your digital logic subject. When you're going to stop. Okay. Then after that, for this one, you can convert, and this is your answer for here. After you done this, you need to make sure that you will make the exponent similar. So if the exponent is not similar, you need to make sure it's similar. You can pick either wise. After you get the value here, after you get the value, this is not normalized. You need to do normalization. So after that, you will get 1 times 2 the power of negative 3 because you add negative 3. You already done the normalization. Check whether your decimal is correct or not because this one is only 0. So no need for you to worry. So that is the answer. Oh, round out means that you need to round out until 4 decimal digit. Okay. Any question? So this is the answer, normalization. Okay, this is the final answer. That is on the addition. Please try to do all the exercise. After that, you have the similar also addition and also subtraction. The multiplication and division is more straightforward as mentioned. What you're going to do, you can directly multiply it. This one multiply with this. What happened to the exponent? You're going to add them together, isn't it? This is for your mathematical things. Very simple one. Add the exponent to numbers. And then after that, you already get the value. After that, you need to do the multiplication. This one multiply with this. This is also a normal multiplication for you. Okay, for this, if only in the question mentions about bias, of course, you need to adding with the biasing value. If not, you just get this value for your exponent. Okay, next. You after you done the multiplication here, this is your normal without a bias. Then what you need to do, you need to do normalization, isn't it? Then you will get plus 1. So you will get this answer. You need to round out until 4 decimal only 1, 2, 3, 4 until here. So your answer will be like this. Okay, so this is on multiplication. I will directly go fast because this is a normal mathematical. Only you need to add on the normalization things. Okay. And lastly, this one is another example. You can try to do what you need to do. Multiply. Here and here will be doing multiplication. This and this will be doing the addition. And if it's considered, then you need to add with single precision, double precision. I forgot 1, 0, 2, 2. Check back. And for this one, after that, you do the normalization. If it's already normalized, no need for you to do anything. And you need to round out. It's depend on the question, okay? Maybe it's going to mention 4 decimal, maybe 5. So if it's asked you to do 4, then you're going to round out until 4 only. And that is the answer. Later on, if you want to convert it to decimal directly, you can solve the solution to get the value. Now lastly, when the division? Division also similar, I guess. This one, you're going to divide directly. But these things, what you need to do, I think you need to deduct for divisions. Okay. So any question? We just cover it anti-multiplication in our COA. Any question? We need to do our small part in our module 3 first before we start our module 1. Lab 1. Because lab 1, there is some information that you need to know from your module 3. Please make sure you try many times to do the exercise, change the value with your friend. and try to do as many exercises as possible. Okay. So if there is no more question, we can end up because just now we just directly no break at all. We can end up our class. Please make sure you scan your QR code. Okay, stay safe and meet you again next week. But please make sure next week you can run the Visual Studio. For those who did not try to run the Visual Studio, you will be get punished in the class. Okay. Okay.
Can you show me the QR code, Doctor?
I did share also in the e-learning.
Oh, all right.
Yeah.
All right, thank you.
Okay, thank you. Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Bye-bye.
Thank you, Doctor.
Okay.